Hey guys, it's Mrs. Rajewski. I hope you guys are doing a good job today and feeling good, ready for some math. Today we are going to talk about Taylor and Maclaurin series. So before we begin, let's go ahead and get our brain juices flowing and let's try this warm-up problem. So pause the video and try it on your own. Okay, so hopefully you guys tried your warm-up already. So let's work with the function cosine of x. So the derivative of cosine is negative sine. Very nice. And then the derivative of negative sine will be negative cosine. The derivative, the third derivative now, the derivative of negative cosine is going to be negative negative sine, which is positive sine. And then our fourth derivative, well, the derivative of sine is cosine. So we're back where we started. It takes four derivatives for us to start from cosine and get all the way back to cosine. Now let's find the derivative at 0. So f prime of 0, that is negative sine of 0. And if we think back to our unit circle, let's see if I can draw one. Oh me, oh my, oh dear. All right, so at 0, our sine value, which is our y value, doesn't go up or down, so we're at 0. So this is negative 0, which is the same as 0. Now, if we've got negative cosine, that's negative cosine at 0. Now at 0, our cosine value, our distance along the x-axis, is 1. So this is negative 1. Now our third derivative, that was the sine of x, so that's the sine at 0. We already figured that one out. The sine at 0 is 0. And then we have the cosine of x, so that's the cosine at 0, which is 1. And then that's going to start repeating itself too. Hopefully that's what you guys got. Easy peasy. So we're starting part 3 of our notes. We're going to be working with Taylor and Maclaurin series. I'm going to put the links for these videos up on my website so you can access it there. I recommend that you watch them. There are some Khan Academy videos. I actually think they're really good and I think they do a good job of explaining it. So if you still have questions after my video, go ahead and check that out too. Whoa, let's bring this back to size. Here we go. So a little bit of theory here. Let's take the power series. So when we were looking at power series, when we were studying convergence, this is what it looked like. And we can expand this series. So I'll expand it out. And if our n value is 0, we're going to substitute a 0 in for all these n's. We'll get c sub 0, the constant, times x minus a to the 0 power. Then if we try and substitute an n value of 1, this will expand out. So our next term is with the n value of 1. So we just replace these n's in our power series with 1s, and then with 2s, and then with 3s, and then with 4s and 5s, and blah, 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 blah. Okay, so we're just expanding it out for every subsequent n value. And then we can simplify. Anything to the 0 power is 1, so that's just c sub 0 times 1, which is just our constant. So really the only change that's here. And we can keep going. So like with any convergent power series, we can take its derivative. So if I take the derivative, I can apply that power rule. The derivative of a constant is 0. The derivative of our variable to the first power is just 1. So then all that leaves us is 1 times the constant, which is just the constant. And power rule time, we can multiply by our exponent. So that's why we get this 2 here. And subtract 1 from our exponent. And then here's how we get the 3 in the front. By using the power rule, multiply the 3 to the front and subtract 1 from our exponent. And so we've taken the first derivative. Cool. Well, you don't have to stop there. Just like in our warm-up, we can continue to take the derivative. So here's our second derivative. So I've taken the derivative again. Ooh, gone to crazy town. And again, if we take the derivative here, our exponent's 1, so we're multiplying by 1 in the front and subtracting 1 from our exponent, bringing it to an exponent of 0. Anything to the 0 power is 1. So we've got 2 times whatever that constant in the front is. And so on and so forth. Multiply by 2 in the front, we get 6. Subtract 1 from the exponent's a little invisible 1 here. And you don't have to stop there because I'm derivating and deriving again. So now we're at the fourth derivative. And we can keep on doing this n number of times. We can find the nth derivative. So as many derivatives as we want to take, we can keep going and going and going. And what we'll see is that we end up with n factorial, so however many that we have here, n factorial times c sub n, whatever that final constant is, plus n plus 1, so the next factorial, times c sub n plus 1, the next constant, and then we're going to continue to go from there. Oh, why does it keep doing that? Okay, let's move this down a bit more. So what if x was equal to a? Well, then this will simplify a bit more, and we would get f of a is equal to the first constant. F prime of a would be the next. F double prime would be the next. And it would continue to expand. Now think about it. I'm just substituting in a value for a constant value for our x, all the way until we get to the nth derivative again. And so our constant is just going to be n factorial, whatever. Notice that when we take the second derivative, that's 2 factorial times that constant. So if we're taking the nth derivative, that's going to be n factorial times the constant. Hence, our constant is just going to be the nth derivative with respect to a divided by n factorial. You might be like, okay, I don't see any division here. Oh my darlings, check it out. If we have this function and I just want to find out what c sub n is, all I have to do is divide both sides by n factorial. And bada bing, bada boom, there you go. Your constant is alone, and we've got the nth derivative of the function with respect to x, all divided by n factorial. See, it wasn't so bad. I know that division came from nowhere, it looked like. So what we can do is we can continue this expansion. So we know that we had that constant in the front, and I'm just taking this from way up above. And now we can figure out what this little constant is in the front, because it's that numbered derivative, so the nth derivative, divided by n factorial. So if we're on the 0th term, this is the original function with respect to a divided by n factorial. In this case, 0 factorial, which is just 1. So our n equals 0 term, here's our n equals 1 term. Notice that our exponent is a 1, our n value is 1, and our derivative is a 1. Here's our second derivative. So we've got our second derivative, our second n factorial, and our exponent is a 2 because this is our n equals 2 term. Then our n equals 3 term, and this pattern is going to continue over and over again forever. So we can say, well, we know that the 0th derivative is the original function, so that's just going to be f of a, and continue from there. So I just simplified that first term. This is what we call the Taylor series expansion. Pretty awesome? I think it is. So Taylor series expansion, here's our official definition of it, of f of x about x equals a is what we just derived, what we just came up with from taking multiple derivatives. Now, When our a value is 0, when we're centered at 0, this is actually called the Maclaurin series expansion. And so we have a separate formula for that. Most people like to start with Maclaurin series. The Maclaurin series is a special type of Taylor series. So it's when your a value is 0. It's always centered at 0. But then if we don't want to center around 0, we'll use the Taylor expansion to center around some other number, which might not make sense right now, but we're going to learn how to work with and write Taylor and Maclaurin series expansions, and then we're going to learn what to do with them. Okay, so today is just going to be all about writing these expansions, figuring out how we can get them written, and then we're going to play with them. So basically, we can use the Taylor and Maclaurin series expansions to write any function as a series of terms. And that's pretty useful when you're trying to find limits, or when you're trying to integrate a function that's really hard to do or is indeterminate. So where did they get these funny names from anyways? Well, from the mathematicians who just discovered them, proved them, presented them. So Brooke Taylor, he was just an English mathematician. He worked at the time that the whole Newton-Leibniz showdown was happening, the calculus wars. And he worked with a Scottish mathematician, James Gregory, and he formulated the Taylor series expansion. Colin Maclaurin, he was a Scottish mathematician, and he's the one that defined the special case. So it's centering it at x is equal to 0. And he was, for a long time, the world's youngest professor until pretty recently when he was beat out by the American Elias Sabur. So, sorry about that, Mr. Maclaurin. So here we go, example number 1. So we're going to write our warm-up problem, f of x is equal to the cosine of x, as a Maclaurin series. And then after we've done that, we're going to use the series to find a series expansion using, instead of cosine of x, changing our angle up a little bit and using an argument of 2x cubed. So here's my plan. I'm going to start by finding the original function at 0, because this is a Maclaurin series. We're going to be centered at 0. And finding the derivatives. I like to find the derivative until it starts to repeat itself. And then find f prime and double prime and triple prime of 0 over and over again. So let's not just talk about it, let's be about it. Now, the cosine of x, I find it interesting because we can take the derivative over and over again. We're never going to get to 0. So here we go. I'm not going to use hot pink anymore. Let's go with blue. Okay. So we're starting with f of x. So f of x is equal to the cosine of x. Now f prime, we did this in our warm-up. The derivative of cosine is negative sine. The second derivative, well, we'll just take the derivative of negative sine of x, which is negative cosine of x. The third derivative, well, the third derivative of negative cosine of x, well, the derivative of cosine is negative sine, and 2 negatives makes it positive. That's going to bring us back to the sine of x. And then the derivative of the sine of x is cosine of x. Now, if you don't want to write 4 little dashes for your fourth derivative, you can just put a little 4 in parentheses. That shows that you're taking the fourth derivative there. And that's what I usually will do. And that's going to bring us back to cosine. Again, I like to write my derivatives out until I start to repeat. So I found my primes. Now I need to find them at 0, since this is a Maclaurin series where a value is 0. So f of 0 is the cosine at 0. This is all our warm-up stuff that we did already. So the cosine of 0 is 1. F prime of 0 is negative sine of 0, which is 0, since 0 times anything is 0. F double prime at 0, well, that's just going to give us negative 1, because we know that cosine of 0 is 1, and if it's multiplied by a negative, that's a negative 1. The third derivative at 0, well, that's going to be 0. And then our fourth derivative, that's 0. Oh, good gravy. Why did it do that? That's a cosine at 0. And we're back again at 1. So I feel pretty good. We're back to the repeating part. So what next? Well, now we're going to use the Maclaurin expansion. Okay, so with the Maclaurin expansion, we're going to basically use substitution and expand this bad boy out. So here we go. I've got f of x is equal to f of 0. Well, I know what f of 0 is. We have it written up here. It's 1. Plus x times f prime of 0. Well, we know what f prime of 0 is. It's 0. Plus, now I've got x squared, just using the formula that we were working with, of x squared divided by 2 factorial times, now I need that second derivative at 0. How nice. It was like I knew I was going to do this, having it all written right there in advance. I like to stay organized, you know? All right, and we can keep going here. I've got x cubed divided by 3 factorial, and now I'm going to take the third derivative at 0, which is 0. And we can keep going. I don't have it here, but I have it here, so I might as well keep going. The pattern is going to still hold true, so that'll be x to the 4th power divided by 4 factorial times our fourth derivative, which is 1. And now I'm just going to write this. Okay, we're going to have it keep going and going and going. And I don't really know what this pattern's going to be yet, so I'm going to hold tight. So I'm going to simplify. I've got my f of x is equal to 1. Now, x times 0 is 0. I don't need to write that 0 down, so I'm not going to. This is going to cancel out. And negative 1 times x squared is a negative x squared. So I'm going to write minus x squared divided by 2 factorial. That's cool. Now, x cubed times 0 divided by 3 factorial, again, if it gets multiplied by 0, it's gone. It's out of there. Bye. Our next term, we've got 1 times x to the 4th divided by 4 factorial. So I'm going to add that. I mean, we can make our little 4 visible, but it's not, or little 1 visible, but it's not necessary. And this is going to go on and on. And in fact, you probably can see I'm going positive, negative, positive. You guessed it. If I would have expanded this out, I'm going to be negative. And that's going to be negative x to the, please say 6th, divided by 6 factorial. And on it shall go. So if I want to write this series expansion, this is the series expansion. If I want to write the actual series, then I could say that this is equal to, well, what is this going to be equal to? I'm going from k equals 0 to infinity. Now, f to the k power, it's not really k power, it's telling us the derivative. So the kth derivative of f with respect to 0. So we could write that. Actually, I'm not going to write that. Instead, I'm going to write what I see. What I see is that my signs are changing every time. So I know I'm going to have a negative 1 to the k power. The reason I'm going to have a negative 1 to the k power is because that's going to change my, my sign every time. If k is 0, then negative 1 to the 0th power is 1. I'm going to start with 1. So we'll say this is where k is equal to 0. Oh my. And this term is where k is equal to 1. This term will be where k is equal to 2. Here's where k is equal to 3. And what I want to write here for my sum is something that's going to generate these values. So right now, this looks great if we start at 0 and go to infinity, and I've got negative 1 to the k power. This works great for k equals 0. But when k equals 1, all I'm going to generate here is negative 1. And that's not my term here. My k equals 1 term has to generate negative x squared divided by 2 factorial. So I'm going to need something more here to write this series. So what can I write? This x to the k power thing? Well, if I use x to the k power, don't write that down. If I use x to the k power, for my 0th term, so when k is equal to 0, I'm still pretty good because x to the 0 power is going to give me 1. But when I go to my k equals 1 term, when I substitute a 1 in for my k, I'm going to get x to the 1st power. And this is supposed to be x to the 2nd power. So what can I do? I can multiply k by 2. So now you can write this down. Okay, now check it out. Things have not really gotten so crazy because if k is equal to 0, this would still give me x to the 0 power, which is still 1. Fantastic. And if k is equal to 1, I've got a negative 1 here. And if k is equal to 1, I've got a square here. So I'm generating this thing. What about if k is equal to 2? Am I generating an x to the 4th power that's positive? Well, let's see. Negative 1 squared is positive 1. And x to the 2 times 2 power is x to the 4th. Don't hold your breath here. We're not done because we're totally ignoring the denominator here, this factorial thing. Well, that's just going to be k factorial. So this is giving us a little hint about how we can write it. And hopefully I explained this thoroughly for you. So again, I used a negative 1 to the k power because of alternating signs, and I used x to the 2k power because I had those even exponents and I needed that. But hold on a second. Check this out. If k was equal to 1, I would get a 1 factorial here. So I don't want just k factorial. I need 2k factorial. Oh dear. 2k, and this is important, put your factorial in the parentheses because, or put the factorial on the outside of your parentheses, because if you put it right next to the k, then only the k is going to get factorialized. I'm just coined a term. That's the only one that you're going to take the factorial of. So we want to actually take this whole product 2 times k and multiply that by the factorial. Otherwise, I would get 1 factorial, 2 factorial, 3 factorial when k was 3 or 2 or 1. And really what we need is that even factorial. Does that make sense? But we're not done yet because this question asks us to use the series to find a series expansion for the cosine of 2x cubed. So in order to find the expansion for the cosine of 2x cubed, basically all you're going to do is substitute in a 2x cubed for every x that we just wrote up here. So let's write that down. To find the expansion for the cosine of 2x cubed, sub in 2x cubed for all x. Then we're going to have the cosine of 2x cubed is equal to 1 minus, well, I've got x squared. No. I've got 2x cubed squared divided by 2 factorial plus x to the 4th divided by 4 factorial. No, I've got 2x cubed to the 4th. That looks like a 9. I don't know why it keeps doing that. Divided by 4 factorial. Then we are going to subtract, and we've got x to the 6th. Nope, we've got 2x cubed to the 6th divided by 6 factorial. And on it shall go. So we can simplify this a bit. And we're going to get 1 minus, let's see, 2x cubed squared is 4x to the 6th, and 2 factorial is 2. 2x cubed to the 4th power, so we're going to raise 2 to the 4th power, and x cubed to the 4th power. We're going to get 16x to the 12th, and 4 factorial is 4 times 3 times 2, which is 24. Then minus, 2x cubed to the 6th. That's going to be 2 to the 6th is 64. And x cubed to the 6th power is 18. And 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, that is 720. And this pattern shall continue on. We can simplify it a bit more. So let's see, 4 divided by 2 is 2. 16, well, they don't go in evenly, but it does reduce. Let's see, 4 goes into both, 8 goes into both. That's going to give me 2x to the 12th, and 8 goes into 24 3 times. So 2/3 x to the 12th minus, 64 and 720. They are both divisible by, I think, 16. That will reduce to 4x to the 18th divided by 45. So this is our expansion. If we wanted to write the series, we could do that too. Let's just look at our original series that we had written. So it was -1 to the k power. So I'm going to use that again because I still have that alternating sign. And then it's got x to the 2k power. Well, our x isn't x anymore. Our x is 2x cubed to the 2k power. All divided by 2k factorial. Don't substitute in the 2x cubed for the k. That would be wrong. This is your series. So if you're asked for the series expansion, write the expansion out. If you're asked for the series, then write the series. I think the series is a little bit more complicated because you kind of have to think about how am I going to generate this again. But you have all the skills that are necessary to be able to do that. Let's move on. So we just tried this for cosine. Fantastic work. But now we're going to try it for sine. You think we'll get the same thing? They tell us here in this problem, this is a Maclaurin series. So remember, that means that we're going to be centered around 0. So I want you guys to pause this video and try it maybe on a whiteboard or on a piece of scratch paper on your own. See if you get it right. Here we go. I always like to start off by writing all the derivatives down. So the original function is sine. The first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. And the fourth derivative is going to be when it starts to repeat itself again. My 4's keep turning into 9s. I don't know why it does that. And since this is a Maclaurin series and we're going to be centered around 0, I'm going to find f of 0. So f of 0 is 0 since the sine of 0 is 0. First derivative at 0, that's going to be 1 because at 0 cosine is 1. The second derivative, well, 0 times a negative is still 0. The third derivative at 0 is going to give me -1. And your fourth derivative at 0 is back to 0. So we have repeated ourselves. Now, since this is a Maclaurin series, I'll use the formula for Maclaurin expansion. Here we go. And I'm just using our method that we had talked about. So substitute, here we go. And this is asking us to write it as a series. So we've got f of x is equal to f of 0, which is 0, plus x times f prime of 0, which is 1, plus x squared divided by 2 factorial times the f double prime, that's 0, plus x cubed divided by 3 factorial times the third derivative, that's -1, plus, we could keep going, x to the 4th power divided by 4 factorial times our 4th derivative at 0. And this will go on and on and on. So we can simplify that. I got f of x is equal to, well, we don't need to write 0 down, that's 0. 1 times x is x. X squared divided by 2 factorial times 0 is 0. I don't need to write that down. This is just getting multiplied by a -1, so I'm going to subtract x cubed divided by 3 factorial. This is going to get multiplied by 0, so it's going to go away, but we will have the 1 for x to the 5th. You can kind of see that the pattern emerges, right? So probably won't have an x to the 6th, but I bet the x to the 7th will be negative. And I'm just showing off now, so I'll stop and keep going and going. So this is our expansion, which is not what we were asked for. We were asked for the series. So in the series, to kind of write that out for us, remember this is our k equals 0 term. This is our k equals 1 term. This is our k equals 2 term, our k equals 3 term. So when we set up our series expansion, we're going to want to make sure that these are the values that we're generating with a k value of 1. And this is what we're going to generate with a k value of 2. It's a nice way for you to be able to check your work. So let's write our series now. The sine of x is equal to, I'll go to infinity, starting with a k equals 0, since that's how I'm labeling it. Now, I do have alternating signs. So back when we were learning about alternating series, we learned how to write those. We could tell that they were alternating because they had -1 to the k power. Now, my first number here is starting with a positive. So if k is equal to 0, that's going to start me with a positive number because -1 to the 0 power is +1. So I feel pretty good about this. Now I'm going to multiply it by x to the k power. Well, x to the k power is nice, but I already know that if I do x to the k power for a k equals 1, I'm not going to get 3. Instead, maybe I should write something like x to the 2k plus 1 power. See, if k was equal to 1, 1 times 2 is 2, and 2 plus 1 is 3. That's how I generate that. And if k was 2, 2 times 2 is 4, and 4 plus 1 is 5. And if k was 3, 2 times 3 is 6, plus 1 is 7. So using some of those rules that we learned back when we were talking about sequences and series way back in year 1 to come up with that. So I feel pretty good about x to the 2k plus 1 power. That's going to generate this term here, that odd term. But how about that denominator? Well, it's going to match our exponent. So whatever you have down below, That's going to be our exponent. That 2k plus 1 will generate the exponent. It'll generate your denominator as well, but it has that factorial there, so don't forget, put your factorial in. And that's it, we're done. This is the series. It's a lot faster the second time around. And it's going to go even faster for number 3, so here we go. Woo! Problem number 3. Again, we're asked to work with the Maclaurin series, so we're centering it around 0, so make sure we'll use the Maclaurin series expansion rules. And we're working with e to the x power, one of my favorites. Love that natural base. And we're going to use that to find e to the 2x power. Okay, so you know me, I like to start with the original function, f of x. And usually I'll keep going and taking derivatives until it starts to repeat. But that's one of the cool things about the natural base, is that the derivative is itself. And it'll go on forever, just being itself. All right, I'll stop here. Now we're going to find f of 0. Well, f of 0 is what we get when we substitute in a 0 for the x. So I've got e to the 0 power. Well, that's 1. And then f prime of 0, well, again, that's e to the 0, and that is also going to be 1. And f double prime at 0, again, you heard it here, folks, 1 again. So since we're using the Maclaurin series, we're going to expand this out. And I'm still following my rules for my method here. I'm just going to substitute what I've got in. So here we go. We know f of x is equal to e to the x. And that's going to equal f of 0, which was 1, plus x times f prime of 0, which was 1, plus x squared divided by 2 factorial, times the second derivative at 0, which is 1. And we can see the pattern. Oh my. We're just going to keep multiplying it by 1 every time. So if I simplify this, I've got 1 plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial. And this is asking me for writing this as a series and then writing it as an expansion. So looking at this pattern, I don't see that I'm getting any alternating signs. So I don't really have to worry about that. Let's see, we've got a k equals 0. Well, don't have to worry about alternating signs, so it's just x to the k power divided by k factorial. Let's see if that would work. If k equaled 0, that would be this term. X to the 0 power is 1. 0 factorial is 1. 1 divided by 1 is 1. Very good. If k is 1, that would generate this term. X to the first power divided by 1 factorial, that's x. If k equals 2, x to the second power divided by 2 factorial, I think we've got a winner. Of course, we're not going to stop there, because now we need to find the series expansion for f of x is equal to e to the 2x power. And that just means we're going to substitute in a 2x for every x that we had up here. So f of 2x is e to the 2x power, which is 1 plus 2x plus 2x squared divided by 2 factorial plus 2x cubed divided by 3 factorial, and so on and so forth. And we can actually say that that equals the sum. I'm going to go a little bit more than I said that I would. I'm going to go ahead and write the series instead of just the series expansion. And this is going to be just the original with a 2x instead of an x substituted in. See, these start to get a lot easier once you get the hang of it. Hopefully you're getting the hang of it. So let's try this example number 4. So we're supposed to find the Maclaurin series for f of x equals ln 1 plus x. And this is a little different because it's not just like our straight up function. We've got a little action in the argument here. But don't freak out, it's not too bad. We're going to start it the same way we've done before. We've got f of x is equal to ln 1 plus x. The first derivative isn't so bad. We know the derivative of the natural log is 1 divided by the argument, so that's going to be 1 divided by 1 plus x. But I'm going to write this with exponents so it kind of looks more like a power series. That's like saying 1 plus x to the negative 1 power, right? And now that it's written in that format, it's going to be a lot easier for me to take the derivative over and over again because I can multiply by negative 1 out to the front. Then we've got 1 plus x, and we subtract 1 from the exponent, so that's going to give me negative 2. We could take the third derivative. Negative 2 times negative 1 is going to be positive 2. I'll even write 2 times 1, why not? And then we've got 1 plus x, subtract 1 from the exponent, that'll give me negative 3. To find the fourth derivative, I'm going to multiply negative 3 out to the front, so that'll be negative 3 times 2 times 1 times 1 plus x, and subtract 1 from the exponent. I'm going to go crazy. I'm even going to take the fifth derivative. What? Somebody stop her. And with the fifth derivative, notice I'm going to be multiplying by negative 4 to the front. So a negative times a negative is a positive. And that's going to be 4 times 3 times 2 times 1. You guys seeing it? It's a factorial. So we're going to write it as a factorial. And hopefully you saw that before I said anything. You guys are pretty smart. I'm sure you did. And notice, when I have the fifth derivative, my exponent is that 5. But I have 1 less out in the front. Okay, so maybe that'll pop up again. Now let's see. We are looking at the Maclaurin series, so I'm going to be centered around at 0. So we're going to find f of 0. So f of 0 is ln 1 plus 0. Well, ln 1 plus 0 is 1, so ln 1 is 0. Gotta love that. All right, the first derivative at 0, that's going to be, well, 1 plus 0 is 1. To the negative 1 power is 1. Second derivative at 0, that was negative 1 on the outside times 1 plus 0 is 1 to the negative 2 power. So I'm just substituting a 0 in here to that second derivative and simplifying. 1 to the negative 2 power is still 1, and 1 times negative 1 is negative 1. Third derivative at 0, I have 2 times 1. I'm going to write that as 2 factorial. Hopefully you guys are cool with that. And 1 plus 0 is 1 to the negative 3 power. Well, 1 to whatever power is going to be 1. So 1 times 2 factorial is 2 factorial. Do you have a guess at the fourth derivative at 0, what that's going to be? Well, negative 3 times 2 times 1 is negative 3 factorial. And 1 plus 0 to the negative 4 power is 1. So that's just going to be negative 3 factorial. And the fifth derivative at 0, that's going to give us positive 4 factorial. And then 1 plus 0 is 1. 1 to the negative 5 power is 1. So it's just multiplied by 1. We're good. Ooh, we got alternating signs here. Do you see it? The positive, negative, positive, negative, positive, negative, and the factorials. This is great. Okay, so I'm going to move my sign up here for our method. I've just kind of been using our patterns over and over again, so I haven't been referring back to the method. I hope that's okay with you guys. So here we go. We're using a Maclaurin expansion because this was a Maclaurin series. And here we go. I've got f of x is equal to, f of 0. Well, f of 0 was 0, so we're going to use that, plus x times f prime of 0, which was 1. Easy peasy. Then x squared divided by 2 factorial times double prime of 0. So double prime of 0 was negative 1. Plus x cubed divided by 3 factorial times the third derivative at 0. So that was 2 factorial. Plus, and we're going to continue it out. Since I did 5 derivatives, I'm going to go ahead and expand it out the 5 terms that I did. So that's going to give me, let's see, x to the 4th divided by 4 factorial times that 4th derivative. That's negative 3. Let's just write negative 3 factorial because the negative's on the outside. It's the 3 that's getting the factorial on it. And x to the 5th divided by 5 factorial. And we're going to multiply that by the 5th derivative at 0, which is 4 factorial. And this pattern is going to continue going. So I like to put the plus dot dot dot, so that indicates that that's going to continue expanding. Now I'm going to simplify, and I just want to remind you, I love simplifying with factorials anyway, but here's 3 factorial. Remember, that's 3 times 2 factorial, right? And then this 2 factorial and this 2 factorial will cancel out. And 4 factorial is really 4 times 3 factorial. And then this 3 factorial cancels out that 3 factorial. And don't forget, it's still getting multiplied by a negative, all right? 5 factorial is 4 times, 5 factorial, I was looking up here at this 4, is 5 times 4 factorial. And our 4 factorials reduce because any number divided by itself is 1. So when I rewrite this out now, it's going to look much different. I don't need to write the 0 again. 1 times x is x. Negative 1 times x squared is negative x squared. And 2 factorial is just 2 times 1, which is 2. Now over here, I've got plus x cubed. The 2 factorial canceled out the 2 factorial, and it left me with the 3 in the denominator. Here, when the 3 factorials canceled out, I was left with the negative, so I'm going to multiply that by x to the 4th. And since the 3 factorial canceled out, it left me with 4. Here, we've got plus x to the 5th divided by 5. And I think you can see a pattern beginning to emerge. So this one's a little trickier to write our series. So we've got our expansion here, but now I need to write the series. So let's see what we've got. I'm going to go from k equals, I'm going to start at k equals 1. I'm going to start at k equals 1 so that I don't end up getting a 0 in the denominator. You might find a way to write it with a k equals 0, and that's cool, but I'm going to use a k equals 1 to start with. Now, I do notice that I have alternating signs, so I'm going to need to use my alternating series situation, negative 1 to some power. Now, if I use negative 1 to the k power, and k is 1, then I'm going to start with negative 1. But this doesn't start with a negative. It starts with a positive. So I'm going to use k plus 1. This will say if k is equal to 1, then 1 plus 1 is 2. Negative 1 squared is a positive. So I'm leading with the positive, and that's going to continue to generate the change in sign every other one. So I feel like that's pretty good. Now, what am I going to multiply it by? Well, I need an x, right? I don't want just a positive 1. I need an x. So x, but let's maybe make that x to the k power, because x to the first power does give me x. And then I'm not going even or odds. I don't have to do anything fancy to change my exponents. Just whatever k value I start with is what exponent I'm on. Maybe it would be helpful if I showed you. This is like where k equals 1. Here's where k equals 2. K equals 3. And again, I'm starting this one at 1 instead of at 0 like the others, just so that I don't have a 0 in my denominator. You could probably write it another way. All right, now I've totally ignored my denominator, but that's not so bad because I'm sure you didn't ignore it. What's your denominator going to be? Did you say k? I hope you said k. So this is our series. It's beautiful. I love it. I'm just going to write a little note so we have it in our notes. I started at k equals 1, so I didn't have a 0 in the denominator. I used the negative 1 to the n power because of alternating series. And I'll just say signs. And then instead of using n, I used k plus 1 because I wanted to start with a positive. All right, I've got one last one for you. You might be thinking, okay, the name of this lesson is Taylor and Maclaurin series, and all you've done are Maclaurin series. Ryeski, I need help with the Taylor ones. Yeah, the Taylors are a little bit more difficult. I'd say a little bit, not like a lot, a little bit, because they could be centered around any number, not just 0. And 0 is an easy number to work with. Like, I like substituting zeros. 0 is easy to add, subtract, multiply. Don't you divide it. But it's an easy number to work with. So we saved that one for last. So find this Taylor series expansion for f of x equals ln x, centered around the point x equals 1. So how's this method going to change now that we're using the Taylor series? Well, Taylor series are not centered at 0. They're centered somewhere else. And in this case, they want us to center at 1. So for our method, that's going to change it up a bit. We're going to find f of 1, not f of 0. We'll find f prime of 1, and f double prime of 1, and f triple prime at 1. We're just going to use 1 instead of 0. Okay, so that's it. That's the only big change here. And of course, we're going to use the Taylor series formula instead of the Maclaurin series formula. So let's go for it. Starting with f of x. Well, f of x is equal to the natural log of x. Okay. F prime of x. Well, the derivative of the natural log is 1 divided by the argument. And I can rewrite that kind of like a power series. So I've got x to the negative 1 power. Okay. Double prime, second derivative, multiply by negative 1 out to the front, and then I've got x to the negative 2. And we're going to keep going. Third derivative, multiply by negative 2 in the front, I'm going to get 2 times 1 times x to the negative 3, and beyond. Negative 3 times 2 times 1 times x to the negative 4, That's the fourth derivative. I actually saw it make that little line there. Okay, that was a big 4 for an exponent. Oh, let's do one more. Why not? Fifth derivative, anybody? You don't get to work with fifth derivatives very often. Let's go for it. So negative times a negative is a positive, and I've got 4 times 3 times 2 times 1. I don't want to write all that. This is a 4 factorial, and this will be x to the negative 5 power. Okay, so now we're going to calculate these values about what we're centered at. So I'm not going to do f of 0. I'm going to do f of 1. So that's going to be the natural log of 1, which is 0. Hopefully you knew that. First derivative at 1, well, that's going to be 1 to the negative 1 power, which is 1. Second derivative at 1, that is negative 1 times 1 to the negative 2 power. So 1 to the negative 2 power is 1 times negative 1 is negative 1. Third derivative at 1. Again, just substituting 1 in for our x here. I get 2 times 1 times 1, which is 2 factorial. Hey, look, when you see factorials, write them. Our fourth derivative at 1. I think the program just really wants to make it a 9. I don't know. So the fourth derivative, I've got negative 3 times 2 times 1. That's going to be negative 3 factorial. And then 1 to the negative 4 power is 1. Beautiful. And the fifth derivative at 1. That's going to give me 4 factorial. And then 1 to the negative 5th power, that's 1. And we can see that this is going to continue along on this pattern as we've talked about. So this is a Taylor series, not a Maclaurin series. So don't use the Maclaurin series expansion. Let's use the Taylor series expansion. So that's this guy right here, just in case. So bring this back up. Here we go. Here's our method. So I've got f of x is equal to f of a. So remember, our a value is 1, so we're going to use f of 1. That's 0. Plus f prime of a divided by 1 factorial. So f prime of a, that's this guy, the first derivative at 1. So that's 1 divided by 1 factorial times x minus, I was about to write a. Our a value is 1. Okay, plus, now our second derivative. Okay, that was a negative 1 divided by 2 factorial times x minus a squared. Oh, look, the 2 and the 2, pattern we can use to our advantage. Okay, third derivative was 2 factorial divided by 3 factorial times x minus a cubed. Plus, we're going to continue. Now we've got that fourth derivative at 1, so that's going to be negative 3 factorial divided by 4 factorial times x minus 1 to the 4th plus, let's see, 4 factorial divided by 5 factorial times x minus 1 to the 5th, and so on and so forth. So let us simplify a bit here. 2 factorial divided by 3 factorial. Remember, 3 factorial is really 3 times 2 factorial, and the 2 factorials will cancel out. 3 factorial divided by 4 factorial, well, 4 factorial is really 4 times 3 factorial, and the 3 factorials cancel out. Don't forget that minus sign is there. It's going to just change the sign whether we're adding or subtracting here. 4 factorial divided by 5 factorial, how nice. That is 5 times 4 factorial, and 4 factorial divided by 4 factorial is 1. So we've got some simplifying that we can do here. So I've got f of x is equal to 0, I don't need to write again. 1 divided by 1 factorial is 1. So I got x minus 1, right, to the first. Minus 1 divided by 2 factorial. So let's just say 1 is multiplied to the front here. I got x minus 1 squared. And 2 factorial is 2. Plus a 1 left again in the front, and I'll just say that that's going to be an invisible 1. And when those 2 factorials canceled out, I was left with a 3. Here we had the negative times the positive, which is a negative. And I've got x minus 1 to the 4th divided by 4, since those 3 factorials canceled out. Plus, looks like x minus 1 to the 5th left, and then a 5 in the denominator since the 4 factorials canceled out. And this pattern is going to repeat itself. Now check it out. I'm going to just lift this up a bit for us. This is like our k equals 1 situation. And this is like our k equals 2 situation, our second term. And our k equals 3 situation. If you want to, you can try and start with 0, but I'm starting with 1, especially with these natural logs, because I don't want to end up with a natural log of 0. I just I don't. You could probably do it. I'm just starting with 1 here. Okay, so how would we write this as, let's see, it's asking us for the expansion. Well, here, I mean, our expansion is pretty much done, and we could say what it looks like is happening here. It looks like if we had that dot, 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 that I could keep on expanding this over and over again. I'm going to have that alternating series. Since I'm starting at 1, I'm going to need an n plus 1 or k plus 1, however you like it. Yeah, let's go ahead and make it a k. Okay. Then I've got my x minus 1. Very good. And if this is k equals 1, oh, this is an exponent of 1. This is k equals 2. This is an exponent of 2. So I'm going to raise this to the k power. And then the whole thing, right, is being divided by k, whatever k value we have. So, and then I'm letting you know that this is where n is, or I should say k, is going to be greater than or equal to 1. And again, we started with a k plus 1 because if I started with a k equals 1, we want that negative 1, we want it to start with a positive instead of with a negative. So that's that. And my darlings, that's what we have. That's what I have for you today. This is what Taylor series and Maclaurin series expansion looks like. So we know what it is. We can generate one. How do we use it? That's going to be the next time. So go ahead and go to Khan Academy, do the assigned practice. I already put it into your assignments on there, so you could just do this real quick Google thing. Make sure you're logged in with your school email so that you can do that. And then try that particular Khan Academy to get yourself some practice. I'm going to do another video on how we use it, and then you'll be prepared to do the actual homework on My Lab and Mastering. Take care, you guys. I wish I was seeing you in person to do these because they're so much fun. And good luck. I'll see you next time.